Hi, everyone. I'm Yenzo from Cleveland Clinic's Cognitive Health Science Department. Today, I'm excited to share our unified deep learning framework for competing risk modeling with functional covariates and building missing data imputation. Let's see how we can improve ICU readmission risk prediction. This work is driven by a real-world ICU study. Before introducing the unified deep learning framework, I will provide some background on survival analysis, and then I will introduce our framework and share results from simulation studies and real case applications. We will conclude with a discussion on our findings and future directions. The title of this presentation might sound a bit complex. I will try to keep simple and engaging. Before we start, let me give you a brief outline. This study is motivated by practical questions and data needs in our ICU setting, and to introduce innovation in methodology and algorithm. But the goal is very simple. We want more accurate real-time predictions for ICU survivors using the metadata we actually collect. ICU stays are expensive and risky. Even after discharge, many patients remain fragile. Spotting who might deteriorate let us involve in early, save money, and most importantly, save lives. This image illustrates a typical patient journey from critical care to post-hospital discharge. Patients come to ICU from various sources and receive treatments tailored to their conditions. This journey involves multiple stages and interventions. Being admitted to ICU means you are in critical condition, and unfortunately, some patients don't make it. However, for those who do, the journey from ICU to hospital discharge eventually going home is a positive outcome. It's a relief for ICU survivors to recover and return to their daily lives. However, sometimes things don't happen as we want. Adverse events after ICU discharge are common, such as adverse drug events and procedural complications. Many patients can have serious consequences like readmission, longer hospital stays, and even death. Studies show that around 20% of patients face these issues within 30 days of discharge, and in severe cases, patients who initially recover might deteriorate and need to be readmitted. This study from the surgical ICU shows that readmission significantly impacts patients' outcomes. For example, mechanical ventilation days increase from around 4 to 10 days, and the second ICU stays can extend from 3.7 to 14.3 days. And overall hospitalization can extend from 19 to 45 days. This also leads to a significant increase in hospital mortality from 5% to 20%. The most adverse events after ICU discharge is mortality, whether it occurs in a hospital or at home. A long-term follow-up study published in 2023 found that compared to the general population, ICU patients experience significantly higher mortality rates across all age groups from 18 to 50, 50 to 65, 65 to 80, and 80 plus. In conclusion, what motivates our study? Patients discharged from the ICU remain at high risk for adverse outcomes, and we want to model time from discharge readmission while accounting for death as competing risk for ICU patients. Modeling these outcomes can enhance patients' care through early identification of high-risk patients and reduce readmission rates. We've talked about competing risk in our previous slides, so now I will break it down. Competing risk is a term used in the survival analysis to describe an event that either prevents or fundamentally alters the probability of the primary event happening. In our cases, why are death and readmission competing risks? When a patient dies, they are no longer at risk of being readmitted, and in other words, death competes with readmission. Ignoring death would inaccurately inflate the estimated risk of readmission and could lead to misleading conclusions. Also, what is functional data? Functional data, which is also called waveform data, can be thought of as continuous records or curves collected over time rather than single numbers. For instance, if you record a patient's heart rate every second over the course of a day, you end up with a curve that shows their heart rate at each moment, and that for curve is what we call functional data. Okay, so we have known a little bit more about the terminology, computing risk, and functional data. I think we are ready to discuss the unified deep learning framework, which our project focuses on. Okay, so here's what we have in the real-world setting. To do that, we are working with rich real-world data. This includes functional waveform data like heart rate, respiratory rate. We also have information on demographics, comorbidities, treatments, and lab results. The key thing we want to do is prediction. What makes this so challenging, and why do we need a unified framework? There are two main problems we are facing right now. The first one is multiple competing events, and the second one is diverse data sources, which introduce high dimensional and complexity. We have demographics, clinical variables, and continuous waveform data. And the third problem is we have frequent missing data. Like, for example, we have lab tests that is not recorded. And the last problem is that we have time-dependent treatments, such as interventions that changes hourly or daily. That's to say, we have a need for advanced modeling techniques to handle the high-dimensional and heterogeneous data. Given all that said, we propose a single end-to-end network that learns competing risk hazards, handle functional curves, and handles the missing data all at once. Conventional feed-forward neural networks for discrete time survival modeling cannot fix the problems that I have mentioned all above. And here's the key update. When you can see from the slides, we have main architecture and basis layers and missing imputation. We have import pair, which consists of patient covariates, patient feature, variables, and indicators. And we also have basis layer and missing value imputation. Our key innovations is these two, basis layer and the missing value imputation. For basis layer, instead of hard coding the blocks, we learn them. Each basis function is a tiny neural network, basically a micro network inside a big network. And for the missing value imputation, we use this novel innovation algorithm called IRO algorithm, and I will introduce these two innovations in the next few slides in detail. And after deep neural network, we have output layer, which gives the parameter of cause-specific model and sub-distributional model. Our learning objectives stay simple cross-trophy. We have the loss function for the cause-specific and the loss function for the fine gray sub-distributional model. The loss function applied to the survival long-form data, so every discrete time event pair contributes. That keeps our gradients honest with respect to the event time structure. Okay, so our first innovation, which is our first fix, is an adaptive basis layer. Rather than projecting the curve onto a fixed set of splines waves, we learn the basis function jointly with the survival network. Each basis is tuned, so its coefficients carry the most signal for readmission or death, not merely for reconstructing the curve. In notation, every waveform is mapped onto a set of learned basis functions, producing the coefficients B sub IV that fits the fully connected stack. Okay, so how do we build a learnable basis? Each function is itself a tiny neural network, what we call a micro network. For a given waveform, we get as B hat sub IV equals the weighted sum of pi we evaluated at tau j times the waveform value at the same tau j. Just a few practical notes. Since this formulas may sound tricky, we have 3 notes. The first thing is this layers are compact. Each micro network is only 2 to 3 dense layers, so the parameter cost is modest. Second is task aware. During backprop, gradients flow from the survival loss to the micro net. So the shapes it prefers are the shapes that matters for the predicting outcomes. Third is interpretable. After training, we can visualize to see which part of the waveform drive risk. The second innovation we have is that dealing missing data with IRO algorithm, which represents the imputation regularized optimization. Traditional imputation methods may not perform well in high-dimension settings due to computational complexity and inability to capture the complex dependencies among variables. And Dr. Liang proposed the IRO algorithm, which we integrated in our framework, in our deep learning framework, to perform missing data imputation and prediction. ICU covariates are high-dimensional, correlated, and often have more than 20% of missing. Of course, one-shot mean and median fields ignore the context and distort the risk estimates. So we treat every missing entry X-miss as a latent parameter optimized jointly with network weights theta. We have 2 complementary objectives. The first thing is data plausibility. Basically, a Gaussian graphic model answers the question, given the covariates you do see, where should this value live? And the second is a prediction utility, which is a survival loss answer the question, what value would make the network hazard prediction more accurate? By having X-miss along with the sum of those 2 gradients, we fill the gaps in a way that's both statistically sensible and clinically meaningful. Here is the mechanics. Inner loop, which is I loop, which is for 2 or 3 micro iterations. We update each missing entry via the gradient rule we see on the slides. The first gradient comes from the GGM and the second from the survival head. And there's also an outer loop, which is called the RO loop, it gives, with the imputation frozen for this batch, we run a standard forward-backward pass to update the weight theta. If we are using a sparse GGM, we also refresh its age set to the graphical lasso. We stop once both the loss and the imputation become stable. In practice, this set adds about 15% of training time, where was a jump in accuracy. So here's the takeaway for the IRO algorithm. IRO means we never rely on a stable, potentially basis biased imputed dataset. The fields involved with the model, giving the sharper risk predictions for ICU readmission and post-discharge deaths. Okay, let's move on to the last section. We worked with 3 datasets, a synthetic cohort of 1,000 patients, and 2 real-world ICU cohorts, the open source MIMIC3 database, and a Cleveland Clinic ICU internal dataset. These 2 real-world datasets have more than 17,000 ICU stays, and we compare our model with 2 baseline models, random survival forest and traditional competing risk regression. The performance is judged with the integrated Braille score IBS. A lower IBS means a better prediction results. And we focus on half-year and 1-year horizons because they map to real ICU planning circles. And here's the result of the simulation. The cleanest scenario with no missing values, we find out FCRN attains the lowest mean IBS for both cases under fully observed conditions. And for 25% and 55% missing training data, we find out like FCRN with learned MVI, which means missing value imputation block, remains generally the best. For 50% missing at random, FCRN beats the median imputed FRSF and competing risk by more than 0.002 IBS. The bottom line is this network is robust to missing data and uniquely able to help with functional predictors. Let's move into the MIMIC 3 ICU cohorts, which is roughly 17,000 admissions. And we found out FcRn is best in every cell across all horizons, across all models and both cases. And we find out again is most pronounced for readmission, COS1, which is a key clinical endpoint. And for the external validation on CCF cohort, we trained solely on MIMIC data and secures, and we find out the IBS values is lowest even when tested on CCF patients for both half-year and 1-year prediction in COS1, which is readmission rate, and this result is great. And last, the part is discussion. And what we have built FcRn, which is discrete time deep architecture with basis layer for covariate effects. And it also involves gradient-based missing value imputation embedded in training. And it can handle both CSC and FGM hazard model. Why it matters? First, across every dataset, synthetic MIMIC3 and CCF external cohorts, FcRn delivers the lowest IBS in readmission rate prediction. Second, even when we wipe out half of the training values at random, the gradient-based imputation holds the line. The performance barely moved, and the model can read waveforms. It can pose a signal out of functional imports. And last, it generalized to unseen hospital systems, CCF, which underscores the readiness for real-world deployment. Looking ahead, what we will do? We will expand it to multi-center cohorts to broader validation, and we will incorporate real-time data streams for bedside risk updates, and we will also conduct user-centered studies on interpretability and clinician adoption. Thank you very much for my co-workers, Dr. Gao, for his FcRn data training and model build, and thank you for Dr. Wang and Dr. Liang for the instruction and for the ideas. Here's my reference, and thank you very much for your time. And now it's a time for question and answers. Thank you.
Hey, well, thank you very much for a very informative talk. Does anyone have any questions for the speaker? Okay, so a question from Glenda. Do you think genetics could further improve the performance of this deep learning model?
Yes, I think definitely will. If we have the genetics data and we can handle the patient's homogeneity and heterogeneity in their genetic information, it would definitely improve our performance of this deep learning model. Yeah, if we can have them.
Yeah. Now here's another question from Boris. Does predicting a higher readmission rate allow to make some intervention to prevent the readmission?
Oh yeah. So the question is, yeah. So it's basically like this. Maybe we can tag the patients who have higher readmission rate or possibly could have higher readmission rate, and we can treat them like with more caution and maybe give them special strategy when they are staying at ICUs and given more information for the doctors and the physicians.
Hey, very good. Now, anyone else? Yeah, well, I have a question. You know, the missing data imputation is a problem that has been with us for a very long time.
Yeah.
And, you know, every improvement in our ability to impute missing data is very welcome. But I always wonder with any new method that comes our way, sort of what it does, what its particular strengths are, but which kinds of missing data situations are still going to need further attention. Can you tell us something about that? I mean, particularly the strengths, but the other side as well?
Yes, I would say like for every statistician, like imputation or not to impute is always a big question. Really and especially for the clinical data, imputation is especially a very important question because we don't want to have like um, imputed from what we synthetic, and this it's been pretty tricky question that for a lot of biostatisticians. I would say for our study, the reason why we're doing imputation is that the ICU data usually have a lot of missingness, and we cannot guarantee that the imputation is the best, but based on our model and our model evaluations from synthetic data, the thing is that choosing the right and the good imputation strategy is sometimes helpful for our doing further analysis and doing the prediction.
Very good. Yeah, we need to stop because it's time for closing remarks.
Okay.
So thank you very much.
Okay, thank you.
Thanks to all
Thank
the
you.
speakers, and I'll see you at the closing remarks in a couple of minutes, or in
Thank
less
you.
than a couple of minutes. Bye now.
Bye.